Swayam Prabha. Digital India. Educated India.
Now we can consider the total response of a first order system to sinusoidal excitation. Okay, this is not very different from when we had DC or exponentials, but I'll just go through it in detail once. So when you have, again, taking the same circuit but with a reminder that this is applicable to any first order system, when you have Vp cos omega t plus phi, okay, we know that the force response to Vc, the steady state response, we have calculated this in many ways. It is Vp by square root of 1 plus omega cr square cos omega t plus phi minus tan inverse omega c r. You get a sinusoid at the same frequency but with the amplitude and phase modified. Now the natural response is of the form V naught exponential minus t by RC. Okay, so this is the response of the RC circuit when no input is given to it. Okay, this will always be present. Now this you know from basics of linear differential equation, that the total response can be the steady state response plus a scaled version of the natural response. Okay, now what's the idea here? We have the differential equation governing the system. RC dVc by dt plus Vc is Vp cos omega t plus phi. What does this mean for this function to be the solution to Vc? This value of Vc will satisfy this particular differential equation. Now let's consider RC dVc by dt plus Vc equals 0. Now just to differentiate between these two, let me put a subscript f here denoting the force response and n here denoting the natural response. Now this function here with any value of V0 will satisfy that particular equation. Now let's say we add these two equations, and because the differential is a linear operator, we can add the arguments and so on. We have RC, the time derivative of Vcf plus Vcn by dt plus Vcf plus Vcn equals Vp cos omega t plus phi. So obviously this Vcf here, the force response, plus this natural response Vcn will also satisfy the original differential equation. You see that this differential equation here is exactly the same as this. The coefficients are the same and the right hand side is the same. Okay, so when you compute a force response, that will surely satisfy the differential equation, but that plus any scaled version of the natural response will also satisfy the differential equation, because the natural response after all satisfies the differential equation for 0 input. So in general the solution is the force response or the particular solution that you compute plus a scaled version of the natural response. What is the scaling factor you have? That depends on the initial conditions. Okay. So in this particular case, let's say that the initial condition on the capacitor voltage is Vc of 0. Okay, is Vc of 0. Now we know that the total response is the particular solution There is a unique particular solution, of course. Cos omega t plus phi minus tan inverse omega CR plus the scaled version of the natural response. V0 is unknown yet. Okay. Now we substitute t equals 0 and we find Vc total of 0, which has to be equal to the initial condition that is given, Vc of 0, and that's equal to, substituting t equals 0 in this case, I get Vp by square root of 1 plus omega CR square cos phi minus tan inverse omega CR plus V0. So this unknown coefficient V0 of the natural response is Vc of 0 minus Vp by 1 plus omega CR square cos phi minus tan inverse omega CR. Okay. This you substitute into the solution. This has to be substituted in there to get the total response. Now an interesting thing is, and sometimes it turns out to be useful, that for a given input, that is Vp, omega and phi are given, the input is Vp cos omega t plus phi. Okay. You can choose this Vc of 0, the initial condition on the capacitor, such that the natural response is 0. Okay. If the initial condition on the capacitor happened to be exactly equal to this number, Vp by square root of 1 plus omega CR square times cos phi minus tan inverse omega CR, then V0 will be 0 and there won't be any transients at all. Okay. So if you start from the right initial conditions, and what are the right initial conditions are specific to the input you have, you can have no transient response and you will immediately get the steady state response from the circuit. And sometimes in circuit design this is useful. This is like, you don't have any transients, you start off the circuit from the right state so that you will have only the steady state response. Okay.